Hello, welcome back to my channel. Now, you already know about the concepts, introduction, and everything about big data, including the data processing. Now, let me introduce you to the next chapter, which is chapter 3, introducing big data technologies. So here are the contents for this chapter. There are 6 sections. Started with the distributed data processing, which you already know from the previous video lecture, and also big data processing requirements. I think I already explained a little bit about the big data processing requirements in the previous video lecture, but we're going to have a detailed discussion here. And then after that, we will introduce you to the technologies for big data processing. As for the technologies, as I already told you in the course synopsis, course syllabus introduction chapter and previously, we're just going to focus on the Hadoop and NoSQL technologies. And lastly, in the end of the chapter, I'm going to explain a little bit about textual ETL processing. Okay, moving on. Okay, before we start with the first session, okay, this is a quotes that you might want to think about. Stated here, the first rule of any technology used in a business is that automation applied to an efficient operation will magnify the efficiency. The second is that automation applied to an efficient operation will magnify the inefficiency. Actually, this quote is come from Bill Gates. So I think you might want to think a little bit about these quotes and maybe we can discuss under the comments. Before we proceed to understand how big data technologies work and see associated reference architecture, okay, I think we might want to do a very quick revision on the distributed data processing. Okay, this already has been discussed in the previous video lecture, but this session is very important. You know, we want to see how data and big data technologies has been developed until today. Alright, for the distributed data processing, it actually has been existent since the late 1970s, which is a very long time ago, so 40 years back. And then the primary concept of this distributed data processing is to replicate the DBMS in a master-slave configuration and process data across multiple instances, as you can see in the figure below. Here, this is a distributed data processing in the RDBMS. Okay, each slave will engage in the two-phase commit with its master in a query processing situation. There are several papers on this subject matter. You can Google that. The paper is authored by Dr. Stormbreaker from the University of California at Berkeley departments, and there are also other papers related with this. Right, there are several commercial and early open source DBMS which have already addressed large-scale data processing with distributed data management algorithm. However, this kind of architecture have faced problems in the area of concurrency, fault tolerance, supporting multiple redundant copies of data, and distributed processing program. A bigger barrier was the cost of infrastructure. So the main problem faced by previous studies than the large scale databases was the cost. Of course. Okay, uh, to overcome this kind of problem, that's why they had introduced to this kind of technology that you will learn later. Okay, however, okay, why did this distributed data processing fail to meet the requirements in the relational data processing architecture? Okay, it can be called a hit or miss depending on the complexity of the architecture. The answer to this question lies in the multiple dimension, which is first one is because of dependency of RDBMS. That is why. Okay, the dependency of on RDBMS, there are three here. which first one is SC, stand for atomicity, consistency, isolation, and durability, compliance, quanta selection. And then second one, complex architectures for consistency management, and lastly is latency across the system. Okay, this is there are also others reasons such as slow networks, RD, BMS, input output, SAN architecture, infrastructure cost, again, complex data processing and transformation requirements, and minimal fault tolerance within infrastructure and expensive fault tolerance solution. And this is all the reason why the there are problem with this why data processing failed to meet this requirement in the relational data processing architecture. Right, might want to go to next slide. Okay, due to the inherent complexity and the economies of scale, the world of data warehousing did not adopt to the concept of large-scale distributed data processing. So they didn't want that this large-scale distributed data processing. So on the other hand, the world of OLTP adopted and deployed distributed data processing architecture. Okay, still, okay, the distributed data processing architecture is still adopted by the world of OLTP. Okay, but it is using heterogeneous and proprietary techniques, though this was largely confined to large enterprises where latencies were not the primary concern. Okay, the most popular implementation of this architecture is called client-server data processing, as this figure. I think we already discussed this type of distributed data processing, and one of that, the type of distributed data processing is client-server architecture. So this client-server architecture is adopted by the world of OLTP. Okay, later on you will see GF has also used this client-server architecture concept, but a little bit advanced, they modified it. But we will discuss that on the next slide. Okay, we focus on the client-server architecture first. Okay, the good things, the client-server architecture, it has its own benefits. There are like 5 benefits here, but instead of all the benefit, it also have 4 limitations. This is why it needs an upgraded version. Okay, let's see the benefit first. Okay, first one, the centralization of administration, security, and setup. Second, backup and recovery of data is inexpensive, as outages can occur at the server or client and can be restored. Third is scalability of infrastructure. By adding more server capacity or client capacity can be accomplished. The scalability is not linear. Third one, accessibility of the server from heterogeneous platforms, locally or remotely. And the last one, the benefit is the clients can use servers for different types of processing. Okay, that's all the benefits. There are 4 limitations here. The first one is the server is the central point of failure. It has very limited scalability. Performance can be degraded with network congestion, and too many clients accessing a single server cannot process data in a quick time. So we might want to discard or to improve the limitation here to have a better architecture of the client server. Okay, in the late 1980s and early 1990s, there were several attempts at distributed data processing in the OLTP world, with the emergence of object-oriented programming and object store database. Okay. Here, so they introduced this kind of new generation distributed data architecture. Here you will see the figure after this. Okay, the explanation here, by combining the commoditization of infrastructure and distributed data processing technique, including not only SQL, okay, which is we can say it as a NoSQL, okay, highly scalable and flexible data processing architecture were designed and implemented for solving large-scale distributed data distributed processing by leading companies including Google, Yahoo, Facebook, and Amazon. Okay, so these giant companies, they're the big company that has to deal with a very large data. So they are designing a new architecture that is highly scalable and flexible data processing technologies. Okay, this new generation distributed data architecture has uh, all these criteria, which is first one, extreme parallel processing. Okay, the ability to process data in parallel within a system and across multiple systems at the same time. And the second one, minimal database usage. The new approach to acquire, store, and manage data remove or bypasses the dependency on the database. So they did not want the database to depends on to be dependent. This naturally remove the asset compliance limitation, so all the limitation has gone. The assist in the traditional RDBMS platform. In this new architecture, RDBMS, DBMS, and NoSQL technology have a role and can be deployed as needed to solve that requirement. So they deploy this. And then the third one is this distributed file. Okay, sorry for the typing earlier there. File-based storage. Data is stored in files, which is cheaper compared to storing it on a database. So it's no longer on the database. Okay, additionally, data is distributed across systems, providing built-in redundancy. And then linearly scalable infrastructure. Okay, that means that every piece of infrastructure added will create 100% scalability from the CPU to storage and memory. So we want this scalability. Okay, next is the programmable APIs. All modules of data processing will be driven by procedural programming application, program interface, which is short for APIs, which allow for parallel processing without the limitation imposed by concurrency. The same data can be processed across systems for different purposes, or the same logic can be processed across different systems. Okay, and then high-speed replication, that means the data is able to replicate at high speed, of course. And then high availability, the data and the infrastructure are always available. Okay, we want the data always updated. Okay, and then localized processing of data and storage of result, the ability to process and store that result locally, meaning compute and store occur in the same disk within the storage architecture. This means one needs to store replicated copies of data across disks to accomplish localized processing. And the last one, of course, has to be fault tolerance. Okay, with extreme replication and distributed processing, system failure could be rebalanced with relative ease. It's mandated by web users and application. We don't want fault tolerance in our database, aren't we? So all these criteria in this new generic architecture. Okay, this is how the new generation distributed data architecture look like, as in the figures. Okay, now we will talk about the big data processing requirements. They are, of course, five. Sorry, five. Yes, five requirements in big data, which is 3 V's, as you already learned. There's the must-have in the big data. Okay, volume, velocity, variety, and the other two is ambiguity and complexity. Okay, we started with the requirements based on the volume. Okay, volume, that means the size data need to be processed is large. So, of course, that's why we call it as big data. Okay, data needs to be processed in parallel, same with the new generic architecture before this. Okay, data needs to be processed across several programs, modules. Data need to be processed once and processed to completion due to volumes. And lastly, data needs to be processed from any point of failure. So it has to be fault tolerance. Okay, and then in terms of velocity, data needs to be processed at streaming speeds during data collection. and data needs to be processed for multiple acquisition points. For variety, data of different formats needs to be processed, okay, and then format, type, structure, and regions, all this kind of variety lah. Okay, for the ambiguity, big data is ambiguous by nature due to the lack of relevant metadata and context in many cases. Big data that is within the corporation also exhibits this ambiguity to a lesser degree. And then in terms of complexity, big data complexity needs to use many algorithms to process data quickly and efficiently. Several types of data need multi-pass processing, and scalability is extremely important. Okay, we talk about this scalability a lot, so it is one of the requirements of the big data processing. Okay, after you know all these 5 requirements, then only we can talk about technologies for big data processing, of course. Okay, there are several technologies that have come and gone in this data processing world, from the mainframe to tier databases to virtual storage access method, okay, which are short for VSAM files. Okay, there are also a lot of programming has evolved to solve this puzzle of high-speed data processing. Okay, some of the programming are still there, and some already gone. Okay, this technology is come and gone. So I showed you how for years had been changing a lot. Okay, especially now. Okay, everyday life, all our life in our life, we involve with a lot of data. It's a very big data, and the technologies has to come update lah. Okay, with the internet, of course, and with this internet bubble, so data processing has become very important. Okay, so all these technologies companies like Google, Yahoo, I'm not sure Yahoo is still very popular, but we will look at Yahoo, how they provide the open source project like Nash. Okay, this we will talk about later in the Hadoop. Okay, technology. Okay, and then all these technologies. Okay, they are come out with the fundamental. Okay, the focus of this section is to discuss the evolution and implementation of this technology around these 3 elements, which are data management, data storage, and data movement. Okay, so the technologies, this is actually important things that we will be discussed around the technologies. Okay, we might want to start with the first technologies, which is Google File System. Okay, if you Google File System, there is a lot of things that you can read online. Okay, I don't think I need to explain this, but since you are here, so I have to explain it anyway. Okay, this is a Google GFS architecture. Okay, here down here, you can see that. Okay. A little bit, as mentioned on the Google File System, it is introduced in the late 1990s. Okay, where that time Google was expanding the search processing capabilities to scale up effectively on massive volume of data. Okay, in the quest for performance and scalability, Google discovered that its requirement could not be met by traditional file system. Okay, so they cannot use the old system, and that is why they need another system, and the file system, which is called as a Google File System, is born to meet the demands of the to perform to have an extremely high performance file system lah, to for the large scale data processing. Okay, because Google has to process a lot of large scale data, so they need this kind of file. Okay, so in 2001, Google has published the design concept. Which is called as Google File System. Okay, in short, it's a GFS. Okay, which has revolutionized the industry today. Okay, this is the startup for what happened to the technologies today lah. It also is fundamental for Hadoop. Okay, there are the key pieces of the architecture is shown as a figure, previous slide. Okay, there are two things including in the architecture, which is first one, a GFS cluster, and the second one is a file. Okay, for the GFS cluster, it is a single master. Okay, a multiple chunk servers per master, accessed by multiple clients, and running on commodity Linux machines. And then for the input data files are divided into chunks. Okay, 64 megabyte is the standard chunk size. Each assigned is unique 64-bit handle and stored on local chunk server system as files. To ensure fault tolerance and scalability, each chunk is replicated at least once on another server, and the default design is to create 3 copies of a chunk. So this is the default setting. Okay, for the file, it is represented as file size chunks, labeled with 64-bit unique global IDs, and stored at chunk servers and three-way mirrored across chunk servers. Okay, so these are the two main components in the GFS architecture. The role of the masters is to communicate to clients which chunk server have which chunks and their metadata information. But if there is only one master, there will be a potential of bottlenecks. That's why there has to be another way. Okay, then the client task then has to interact directly with chunk server for all subsequent information and use the master only in minimal fashion. Okay, then this is the only way to avoid the position of master to become a potential of the bottleneck. Okay, another important issue to understand in the GFS architecture is the single point of failure, or for short we call it as a SPOF, of the master node and all the metadata that keeps track of the chunks and their state. Okay, to avoid the situation, the failure, okay, GFS was designed to have the master keep data in memory for speed, keep a log on the master's local disk, and replicate the disk across remote nodes. This way, if there is a crash in the master node, the schedule can be up and running almost instantly. So there is a backup there. Okay, the master, it stores these three types of metadata. First one is a file and chunk names, phone and spaces. Second one is mapping from files to chunk. And the third one is location of each chunk's replicas. Okay, that means the replication of the chunks. The replicas location for each chunk are stored on the local chunk server, apart from being replicated, and the information of the replication is provided to the master at startup or when a chunk server is added to a cluster. Since the master controls the chunk placements, it always updates metadata as new chunk gets written. The master here will keep track on the head of the entire cluster, okay, and then to avoid the crash. But there is a periodic to check on the health on the entire cluster. Okay, also to keep track if there is any data, corrupted data. Okay, due to volume and scale of processing, there are chances of data getting corrupt or still there are chances there because our data is a very high volume. Okay, to recover from this or any corruption, GFS appends data as it is available rather than updates an existing data set, so it doesn't do the updates. Okay, it appends the data. Okay, this provides the ability to recover from corruption or failure quickly. When a corruption is detected with a combination of frequent checkpoints, snapshot, and replicas, data is recovered with minimal chance of data loss. Okay, that's what makes the GFS, the strength of the architecture. Okay, after this we will look at this is the Google file system written by Google people. Okay, you can read the full paper, okay, on the online, or if you are my student, you can read it through Kalam. Okay, this is the strength of the GFS structure. Okay, there are four strengths here: availability, performance management, and cost. For the availability, the triple replication-based redundancy, more if we choose chunk replication, rapid failover for any master failure. So there is a very minimum chances of failure. Okay, and the automatic replication management, in terms of performance, it is the biggest workload for GFS is a read on large data sets, which based on the architecture discussion will be a non-issue. And then there are minimal writes to the chunk directly, thus providing up to availability. In terms of management, GFS manages itself through multiple failure modes: automatic load balancing, storage management and pooling, chunk management, failover management. And lastly, in terms of cost, is not a constraint due to use of commodity hardware and Linux platform. Right, that is all about the GFS. We will discuss on the Hadoop and in a very details in the next video.